Merci. Well, thanks everyone. So I'm going to present our work named Display Aware Image Editing. So Wonky could not be here today, but he did most of the work that I'm going to present. So our motivation is very large images. And when I talk about very large images, I'm thinking to 100 megapixel and above, and typically even gigapixel and larger. And our motivation is that I think since this morning we have seen that it's pretty easy to both create these images by stitching several photos together. So stitching software is widely available. It's also fairly easy to acquire many photos. So for instance, we have seen gigapixel camera this morning. We have seen the gigapans that make it all for you, or even sometimes just going around with a camera and just snapping picture handheld is doable. And to motivate a bit more, I'm going to show you a quick tour through Hong Kong with a panorama that I did by myself by snapping the picture handheld. So I want to go. So here what we see is Hong Kong. So that's typical view from Hong Kong, a lot of buildings, skyscrapers. It's a great place if you have not been there. So let me zoom in to show you a bit more. So here we see these boats. If you ever go there, it's too bad for you because you used to pay 25 cents to just cross the sea and go on one of these, but they stopped them last week. So now it's much more expensive to go there. Here's something else. So every tower in Hong Kong has a story. So here, this one is a Bank of China, and this one is Bank of America. And if you look carefully, this one is spiky. And some people say it's not random. There is some intent in the design of the Bank of China tower. And if I move further, so a lot of towers, and then I arrive here, and this is the convention center where SIGGRAPH Asia will take place this year. So what's nice with these pictures that I didn't, because now the resolution of the projector is a bit smaller, I didn't even done to zoom in to show you a lot of place, and it feels much better, right? We see where we are. And so I want to show something else. So for instance, there's also some challenges. So this picture was not very well adjusted, so I pre-adjusted the picture for that view of the convention center. And arguably it looks better, the contrast is probably a bit better, but if I go back toward, for instance, the Bank of America and Bank of China, it's still not perfect, so I can go here, try to, okay. No, it does not want to show me. Okay, sorry, I lost something in the transition of screen, but the message is what worked well for the convention center does not work well anymore for that view here. That I have several views in this huge panorama. Depending where I look at, I see something different, and it's very hard to have an adjustment that's going to be good for everywhere. So the challenges that are associated with these very large images are they're big. They're just very, very large. There are so many pixels that if I touch all of them, I'm never going to finish. Even a very fast algorithm is not going to end. And as I've just discussed, it's very hard to adjust because what works well at a place may not work well somewhere else because there's so much diversity in these very large images. And that's the problem that we're interested in solving in this talk. So our main idea is that I never show you this 300 megapixel. I told you it was 300 megapixel and you believe me, but I never show you more than 1 megapixel, which is the resolution of the projector here. And that's our key idea. We're not going to process all the pixels, only the pixels that we see. So I'm not going to worry at all about what I don't see if it's not on the screen, or if it's not, I'm not going to worry about the full resolution of the image if I only see a downsample version. I'm only going to process what I see at the resolution at which I see it. So let's quickly look at the literature. So many people have proposed fast filters to do a lot of different operations, and these are great. Just they are designing with the idea that the image is a typical photo with 10 megapixel or 10, 20, 30. But here we're talking a much larger, and all these techniques they still are slow when we're talking about a gigapixel, and they're slow because they touch every single pixel one by one. So they don't scale up to these very large images. So one solution has been proposed a while ago. That's the idea that some operations are local and we can deal with the bounding box and only treat the pixels that have been changed. And even if the bounding box is not visible at all, I'm just not going to run that operation. The problem is that this approach that I proposed a while ago ignores the change, the problem of scale, that we have different scales. So sometimes even a selection may look very small on the screen because I'm all zoomed out, it's still maybe 100 megapixels. And if I run at full resolution, my operation is still going to take forever. So we need to take scale into account. So another source of inspiration is something that Matt just showed 2 talks ago, is this, the work on the gigapixel viewer at Microsoft, where the piece that inspires us is their viewer adapts the tone mapping operator to the current view. So to make sure they have an HDR panorama, but they always show us a good tone mapped image depending on what's on the screen. Here we're inspired by that, but we also want to add user control. We want to let the user decide what the view should be at different places. So here's the outline of my talk, and I will start by briefly discussing a bit our viewer. So here, there is something, because we are going to process only what we see, if we start to cache what has been computed and what has not been computed, it's going to be a real nightmare, because we have a lot of bootkeeping to remember which pixel has been computed and which are not. So we take this very different approach. We say, we are going to process 1 megapixel at every given time. So we are going to recompute it from scratch every time. So no more bootkeeping, no more dependencies to worry about it. Every image is always computed on the fly. And to make that happen, we use GPU, a tile-based hierarchy, and some bounding boxes. I'm going to show that in a minute in a different view. So here our system looks like we have some input images at the beginning, and we don't stitch them by default. We keep them separated. Each of these images is separated into tiles, so that we don't need to load the entire image if we don't need to. Each of these tiles is pre-computed at different resolution, so that we don't need to load the full resolution if we don't need to. All the data are registered in a common X, Y, and scale coordinate system. This red part is a current view. I'm going to load only the data that intersect that view. Then if I have local operations that are represented by a bounding box, I'm going to compute only the one that intersect this viewport. If there's an operation that concerns a part of the image that I don't see, I just don't run it at all. So that's for the viewer, and now I'm going to discuss about the algorithm that works well in this with our approach. And first, I'm going to discuss formally what does that mean to be display aware. That means that we want algorithms such that we can compute the output on the viewing part only on the data that are visible for the same current display. I don't want to use more data than what I see. And there is a detailed proof in the paper, but the bottom of the bottom line is that if we work with Laplacian pyramids and do local processing in Laplacian pyramids, this is guaranteed. We have this property. We don't need more data than what we see to compute the output. So that's a great news because Laplacian pyramids are easy. We all know what it is, and it's pretty familiar and easy to find. It's also kind of a limitation because that restricts the kind of algorithms that we can use, but I'll show you that we can be clever and design algorithms that works with Laplacian pyramids and achieve good results. So here an application. So the same applications that just Matt showed in the first talk of the session. We want to do seamless compositing. We have a bear. We want to put it on the beach, and we want the sim not to be visible. The traditional approach is to use a Poisson equation, and then I agree with Matt. It doesn't scale up. As soon as we have too many pixels, too many variables, it takes forever to solve. So we propose an alternative, which is based on the remark by Forman, which in this paper, what the authors remark is that we need an interpolation, and we need a smooth interpolant. It doesn't need to be the solution of the Poisson equation. Any smooth interpolant is good enough for that purpose. And the interpolant that we propose is a technique that's been known for quite a while, is using Laplacian pyramid and very easy to compute. And in terms of wavelength, it's a classical push-pull if you're familiar with it. So here a little bit more detail. Our input data are a foreground image, a background, and a mask that tell us which part of the foreground we're interested in. We compute the offset along the boundary exactly the same way as Matt before. And the way the algorithm works is first we compute Gaussian pyramid, so assume that we are all we have seen that before. So a Gaussian pyramid is just different resolution by a factor of 2. Then we look at the Laplacian pyramid, where we look at the difference between two subsequent levels. We do that at every level, so we get the entire Laplacian pyramid. If that's the traditional algorithm, to build our interpolant, the only thing that we need to change is how we downsample images. When we downsample images, we need a kernel. The traditional way to use a kernel is to have a square kernel, and we have values everywhere in that kernel. Here we ignore all the values where the offsets are not defined. That's all. That's the only difference that we do, that we ignore where we don't have values there. When we upsample, we use the full kernels as a normal routine. And at the end, here's the result. We upsample, we get an offset that we apply to the image, and we composite. So we have our bear on the beach, and we're happy. So the next thing I want to show is that, is this algorithm really display aware? So for that, I'm going to compare the computation, two ways to obtain a lower resolution of this computation. So here's an image. So this image has two parts. There's the left part and the right part. So first, let me tell you what I did on the left part. The left part, I did the composite at full resolution, and then I downsample the result. So that's the brute force version, because I use all the data, and then I throw most of, throw away 75% of them, because I show you half resolution result. The right part is our technique, where first I downsample. So right away, I discard the data, I ignore them, and then I run our algorithm to only this small set of data. And the good news is that if I didn't tell you that was a half image, there's no, they are exactly the same result. So we achieve our goal. We are able to compute the output of what at this lower resolution using only low resolution data. And to convince you that it's not an easy task, let me show you what Photoshop would do. So same thing. The left part is a brute force version. I run the composite in Photoshop, and it's a gradient domain composite. And then I downsample. So it's seamless. It's no problem. It gives us what we want. But then on the right part, I forced Photoshop to first resample the image and discard the data, and then I did the composite. And as we can see, the result is really not the same. So that's something that no one ever tells you, but Photoshop does not give you the same look depending on the resolution at which you work. The algorithm I just showed you does not have these discrepancies. We always give you the same look at different results. So to show you how it works, so we're going to save Bank of America. We're going to move here. We're going to do a selection. It's about 40 megapixels, and we're going to move it around. We're going to change the zoom level, and nothing is going to remain consistent, which is exactly what we were looking for. The part at the bottom is the interpolant texture. So we move around. It's all interactive in real time, and we can move. Now we're going to change the zoom level, and everything remains consistent. We show you the same result at different results. We just use only this algorithm. And remember, if I were to do that with a gradient domain technique that solves the Poisson equation, we would not have that. As we change the zoom level, we would see some color shift entering the picture. So in the paper, we propose other applications such as panorama stitching, and this summer at SIGGRAPH, we have a paper that show how to do edge-aware image manipulation using Laplacian pyramids. Now I want to discuss more the last part of our work is how do we adjust the viewing parameter depending on what we have on the screen. And the first thing that we did is to better understand the notion of look. What defines the look and the appearance of what we see. And for that, we need a user study. And here our goal is to adjust, but also to give user control, as I explained before. So our user study was pretty simple in principle. We gave pictures to adjust to people. And then we compare the photo before adjustment and after the adjustment. And what we found is that the difference between the color histogram of the image before adjustment and the differences between the histograms before adjustment were larger than after, which means that we have histograms that are all over the place before adjustment. We ask people, adjust this picture in a consistent look to make it look like a postcard. We compare the histogram. Now the histograms are more similar. So that gives us an objective way and a computational way to compare the look of images. This idea was around in the literature before, but no one really tested it, I think, this way with your study. So now we have more solid proof that histograms characterize the look of images and the adjustment that people apply to them. So here's an illustration, two input images that we have here with their histogram. Here after adjustment so that we ask them to look more like a postcard. And they look more similar. I think we can agree that the bottom picture look more along the same line. And if we look at the histograms, they're so better aligned, and we can use Earth movers distance to confirm that these histograms are more similar after adjustment. So the strategy, now that we have this result, our strategy is to adjust the view of that where we move around in this panorama. We're going to adjust the contrast brightness in a way that preserves the histogram as much as possible. That's going to be our computational criterion. Minimize the variation of histograms as we move around. So here's a brief overview of the algorithm. So first we let the user adjust the picture at a few different places. And then we, given a new view that we have no adjustment by the user, we find the adjusted views that are the most similar. We average their histogram that give us a target histogram, and we solve a small optimization problem to find the brightness and contrast settings that best match this target histogram. So I'm going to show you a video, and here what we're going to see is that we're going to zoom at different places in the picture, and some part in the shadows will not match what is in the sun. And at the beginning, our system will be adjusted, so everything will look quite consistent. At some point, we're going to disable our automatic adjustment, and we see that it does not look good, and we'll reactivate it again. And here's the point is that when our system is activated, it looks very natural, and the view quality is, looks very reasonable and almost like we didn't do anything. So here we adjust so that we see the benches correctly. And now we're going to move around. And we keep, it looks, here there's some adjustment going on, but I didn't tell you, I think it would look very normal. So now we disable, so it's too dark. It's too dark because when we zoom out, that's a reasonable adjustment, but it was not reasonable. So we activate again, and if we zoom in, everything adjusts so that we see something correct. So to conclude our talk, I've shown you that we are a strategy to edit very large images, and we tested it on medical data that are larger than a gigapixel, and it works all the same. From an image editing point of view, Laplacian pyramids are key to achieve high performance. From adjustment of parameters, histograms are important and characterize the look of what we have seen. We think this algorithm is particularly interesting from phone and mobile devices because they are small screens, so there's not many pixels to adjust, and our algorithm fits very well in that approach, which is a good news because also phone doesn't have a lot of computation power to offer, so that's a good, there's a good strategy that we have not much computation power, but being display aware does not require too much work to do. So I would like to thank our friend and funding agencies. Also, I don't know if Alyosha is here, but that's his birthday today, so he showed up. I don't think he's here, but if he shows up later, don't forget to thank him, to tell him happy birthday. And yeah, that's the end of my talk. Thank you very much. So there's a part where we, here I didn't discuss it, but we also did, part of the user study also confirms that this strategy reproduce with reasonable, does a decent job at reproducing what user would have done if we asked them to adjust that view. We did a leave one out test basically. So the Photoshop answer say, that's not a good feature for Photoshop. I completely agree, that doesn't fit the story of Photoshop. The way I envision it is that you would choose a kind of zoom level, and then at each location you would fetch a viewing parameter for that view level. And that's a way, in some sense, to define a tone mapping operator. We would find brightness and contrast at every, but you would need to find somehow, and you can think about it because this humongous panoramas this morning, we have seen their best view printed. So one way to decide, you decide at which average distance your viewer is going to be. You choose that and you fix that and you do a tone, you tone map your image, and then you print it. But yeah, it's not, it does not fit the model of editing that Photoshop has, where you have one view no matter what. Yeah.
For the copy and pasting out application, if I paste one region in, I want to duplicate maybe to the other side of the photograph. For that application, your contrast adjustment interpolation system, it would adjust it correctly.
So we.
It would look similar on both sides.
So what we do is that we do the copy paste before any brightness contrast adjustment. These viewing parameters always happen at the end of the pipeline. So what we do, we copy the raw pixel. It's a seamless compositing. And then we take this new, when we go and see that place, we look at that view, compute the histogram, find the nearby images, and adjust brightness and contrast for that view.
So that would come across in a printout?
That would make, meaning the copy and paste can actually at the end be different in a printer. Yeah?
So your histogram is just grayscale, is that right?
So Chemo is, I think it's grayscale most of. Sorry. So yeah, luminance channel. Yeah.
So it seems that you could generalize this to try to do a simple form of white balance compensation. If you have a picture where there's indoor light in part of the image and daylight in another part of the image, you might want to zoom in to one part and to incorporate white balance to make it look good.
Yeah.
Lighting and zoom into another part and have it look good for outdoor lighting.
So I agree. Right now in our prototype, there's no white balance is not one of the parameters we enable, but clearly that's one thing that I envision, and that's one thing where imagine where user control can be interesting. User can decide, you can do indoor, outdoor. That's a classical one. You could decide that one part is kind of a warm mood, maybe happy mood, and one part is more cold and feels sad. And then you would have a more bluish rendition that you can control with white balance. And that's where it's interesting to have the user, because then you can start to have artistic intent in the process to do that.
Any other question? But my old speakers actually. Now please don't take off. I think now we just will have the poster preview immediately. And I will also
Yes. You all know who you are.